guess so. Okay. Thank you for coming. Wow, big audience. So in this session, we'll talk about the evolution of web protocols. Actually, there's a kind of a surprise. Our company sponsored a Nexus 7, so we're going to collect your business cards, and at the end, we'll pick up a winner at the end of the session. So Thomas will run kind of a box through the audience. We didn't expect it to be this big, but we'll try to make it in time, because he had to do the second half of the speech. Will be
maybe I will just pass it around instead.
Yeah. Anyhow, let's start, because it's a very dense presentation, and we have a lot to talk about, and will be really interesting. I hope so for you. So, Thomas and I work for Intalio. Intalio is the company that provides services, support, and training for the Jetty server container, and for another open source project called Comedy. It's a web messaging framework. Intalio also provides an open source solution for BPMS, and we also sell a product to build a business application called Intalio Create. Thomas and I are kind of long-time open source contributor. I started in 2000 with JBoss. I was a contributor at JBoss. Then I went over. I was the project leader of MX4J, other open source project over the years. Currently, I'm the lead architect at Intalio Webtite for the Jetty, and I'm also the Comedy project leader. JVM tuning expert, and Thomas is also contributing to the Jetty project, and also contributed in the past to Grails. Senior engineer at Webtite, is also JVM tuning expert, and mountain biker and climber. And I was a triathlete in my previous life, but oh man, let me cancel this. Okay, so here's the agenda for today. We'll look at the history of the web protocols, how they evolved since they were initially widely deployed over the internet. We'll look at WebSocket for bidirectional web communication, and we'll look at the SPDY protocol, which is the new protocol proposed by Google. And we also look at the end at HTTP 2.0, what will be the future. And if we have time, we'll do a question and answer at the end. So let's start. This one is the page of the w3c.org. It's the front page, like it was in 96, 2002, and 2012. So in 96, this page was one HTML5, 600 bytes. Okay? In 2002, 6 years later, this page became one HTML5, 5 images for a total of 50 kilobyte. So it grew almost tenfold over only 6 years. Now, in 2012, this page is one HTML, 31 images, 4 CSS, 2 JavaScript for a total of 40 resources for 300 kilobyte. That's not even close to the average web page that we have today in the web. Google estimated that the average site has 80 dependent resources on a single web page. Okay? And these are probably spread across like 10 to 30 different domains. And the average weight of this average page is 1 megabyte. So the web has evolved explosively. It's like this one is the graph of w3c.org page in 96, 2002, and 2012. The web content that we deliver today is not even close to what was in 96. Now, can you guess what was the initial first release of the HTTP protocol? What year was that? Was 96. So the HTTP protocol was born to serve simple static web pages, 600 bytes. It's not even close to, nobody imagined that the web would become in this way this year, and so fast. So what else changed during these years? The network, of course. We got better network, better hardware. So in 96, almost nobody had a fast connection. But now, we go here, the average web connection is 4 megabit per second. In the United States and Sweden, probably Europe, most of Europe, it's probably more than that. What else has improved? The network latency. In 96, it was 120 milliseconds to ping your server to get the page. These are also average. Now it's down to 50 milliseconds. Okay, so yes, we had a growth in content, but we had a growth in network capacity too. So are the two comparable? Well, it turns out that we crunched those numbers to try to figure it out if the network was actually growing at the same speed as the content. So we took the 96 page using HTTP 1.0, the protocol that was defined in 96, and it loads in 1 second. Fine. 2012, we take the page of 2012, but still using HTTP 1.0 protocol. So this page loads in 2.6 seconds, which is way worse than what we were, more than 15 years ago. So we have to do something because we cannot grow. So the point here is that the content growth that we had was vastly bigger than the growth of the network capacity.
And just as a side note, W3C.org is a pretty conservative page with few resources only. It's
not the average web page. So let's crunch more numbers and say, okay, but we're not anymore using HTTP 1.0. We're using HTTP 1.1. So what we did was, this one is the previous column, say, okay, what if we use now HTTP 1.1 to load the 2012 page? Well, we could do it in 1.5 seconds. It's worse than what we had in 96. Come on, so let's add more features. So one of the key feature here was persistent connections. Before, we could only do one request per connection, then we had to close the connection. That was HTTP 1.0. In HTTP 1.1, we have persistent connections. So we have, big improvement, 2.6 seconds down to 1.5. Not enough. We're not even close to this one. So let's add another feature. It's called pipelining. Pipelining works in a way that you basically send a request one after the other without waiting for the response. Well, it works. It goes, the load time goes down to 600 milliseconds. But the problem here is that pipelining is a feature that doesn't work. It is disabled in all major browsers, and because it has semantic issues, so nobody uses it. So it was an attempt to improve HTTP, but it failed. So what else? What else we can do? Let's have another improvement here and say, okay, the HTTP protocols mandates that we have a maximum number of connections of 2 connections per domain. Okay, that's the recommendation from the HTTP specification. So what browsers do today? They open 6 instead. All right, per domain. So if we open 6 per domain, what happens is that the time goes down to 900 milliseconds, which is pretty much okay, slightly better than what we did 15 years ago. So what happens? 15 years have passed. Now we have 4 core processors on telephones, but still our load page time is basically the same. Who's to blame here? I guess the protocol, right? So what's the problem with 6 connections? Sorry, I still haven't this pop-up for the Wi-Fi coming. Stops my... So opening multiple connections has a cost. What kind of cost? Well, there's a server-side cost. You have to open multiple file descriptors on the server side. You have to allocate buffers. You have to allocate kernel resources. You have to allocate threads. And you get a number of other things that you don't think immediately, which are, for example, you need to have your load balancer stick all your connection from the same client to the same server. You cannot, open 6 connections and have those spread among your servers, because there's normally some state that you want to keep. You start to have concurrency issues on the server-side code. So you have multiple requests that can arrive to your server concurrently. So for example, if you're using the HTTP session, you have to synchronize on it, because if you modify it, then you may run into troubles, because you modified it concurrently, and that's forbidden by the server specification. So, and then what happens? Well, if 6 connection gave us this performance boost, why not opening 12, right, per domain? It's already happening, actually. What is the most used trick that you actually guys use? It's domain sharding. Domain sharding, it's a trick because you change the domain name, you fool the browser to open multiple connections to multiple domains, but it turns out that all those domains end up in a single server. So you open a browser, maybe you have 3, 4 domains that you are sharding over, and suddenly you don't open 6 connections to this browser, to the server, you open 18 connections per a single browser, right? So that's a lot of things. If you have 10,000 clients, that's a lot of file descriptors. All right, so it's clear now that the content growth, the web content growth, will continue to grow bigger and better than the network growth. We've taken all the nice wins in the network growth, and especially we're limited by the speed of light. We cannot go faster than that. So at a certain point, we will hit a limit on the network. HTTP, the protocol itself, has already been modified to take the easy wins. Not only that, has been bended to actually try to deliver today's web content. So we're starting to bending the rules. We tried pipelining. Oof, that didn't work. And plus, there are people very interested in the internet, like Google, like Twitter, like these big giants here. They are getting, okay, can we do something about this? Because it's broken. These web pages are slow. Can we make them better? So new protocols started to emerge. One of them is WebSocket, and the other one is SPDY, which we'll be talking today. So WebSocket defines a new semantic. We'll go into the details of this. SPDY instead concentrates on improving HTTP and actually replacing it. So let's see WebSocket. WebSocket is an effort that has been initiated by browser vendors. Why was that? Because WebSocket fills a hole that is totally missing in today's web application, which is how do I have servers pushing down contents to client without the client requesting anything? Having idle clients, how do I push data from the server to the client? It's impossible using HTTP right now. HTTP works in a way that the client makes a request to the server and the server answers. Okay? So bidirectional web communication was lacking in HTTP. WebSocket is filling that gap. There were a number of hacks that were employed in HTTP, but all those were hacks. Those are known as Comet techniques, if you heard about before. And of course, we had, Flash, Silverlight, and other bunch of technologies that are now kind of that wouldn't speak for JavaFX, but the other two probably yes. So WebSocket has been standardized. Is now an IETF standard protocol. There is a standard API defined at the W3C, and there is a Java specification request in the working for defining a standard API for server-side application to use WebSocket. So basically, you will have an API very similar to the servlet API to write portable WebSocket applications in your server-side. Just to give you an idea of how simple WebSocket is, this is basically the whole interface that you get in JavaScript on your browser. You get the URL you open the connection to. You have 4 callbacks, functions, that you can assign to these fields. That will be called when a connection has been opened, when there is an error on the connection, when the connection is being closed, and when the server sent you a message. Okay? You will be called by the browser. So this is the passive part. The active part is this tree. You can actually send strings to the servers. You can actually send also binary data to servers. This is a new thing, happened in HTML5. Before HTML5, JavaScript did not have a binary data type. But in HTML5, there are even 2 of them. So now you can actually send binary data to the server. And of course, you can close the connection. How does it work? Oh, crap. All right. Okay, nice. Let me go through this. How does it work? It works in this way. WebSocket runs on the same ports that HTTP use. It runs on ports 80 if you're talking plain text, or it runs on 443 if you're using TLS and you're encrypting WebSocket. The initial step of a WebSocket web application is HTTP. There is a special HTTP request containing special headers that say to the server, hey, I want to upgrade this connection to a different protocol. This mechanism was included in HTTP 1.1 specification, and it's being used here in WebSocket. The server replies with a special response called 101, switching protocols, instead of the usual 200 OK. So it's a special code. It upgrades the connection as well. And what happens next? That on this physical TCP connections, the next thing that will run over that connection is not anymore HTTP, but it's a WebSocket frame. Okay? So a WebSocket frame is binary, is not a text protocol like HTTP is, so it's something completely different. We'll see how this may cause problems. How does a WebSocket frame look like? You don't have to be scared by this. The really important thing is these 2 bytes here. This one are the minimum bytes that are needed in order to define a WebSocket frame. So the overhead of the WebSocket protocol is really, really small. It's just 2 bytes. Imagine the HTTP protocol, okay? It's a normal request, a GET request as GET space / space HTTP1.1/r/n. And it's already only the first line. Then you have all the others. So you didn't even started to ask things to the server, and you're already past 15 bytes or something. The usual HTTP request is something like 500 bytes up to 1 kilobyte. So it's very efficient. This is a benchmark that we run using Jerry 7 and Comet D, simulating a chat application using HTTP. Okay, so here we have these lines here are 20K client connected to a single server, sending 50K messages per second. That turns out to be roughly 40K request responses per second in Jerry, with an average latency of 150 milliseconds, more or less. That's what Jerry can do. That's HTTP. Now let's take a look at the WebSocket, same graph, same application, different protocol. This is the not 20K clients. This one is 50 clients, 50K clients. This one 100K clients connected to a single server, running 50K messages per second, but now the latency is 4 milliseconds. I could not even draw these 2 graphs one atop the other, because this graph here would be totally smashed into the x-axis. So where does this performance boost come from? There's only one thing that is different here. It is the protocol. All the rest is equal. So the key thing is that the WebSocket protocol is so efficient. The server has so much little work to do in order to parse WebSocket and figure it out, that this alone gives you an incredible boost in performance. You go from 20K clients to 100K, and from 150 milliseconds to 4 milliseconds. Is it deployed? Because we're talking something that, yeah, it's new. Can I actually use it? Because maybe not. It turns out that yes, it's deployed. Basically, every browser on Earth support WebSocket. On the server side, we have Jerry 7, 8, and 9 supporting WebSocket. We have Glassfish, Resin 4, Tomcat. Last time I looked, the Tomcat status for WebSocket support was defined alpha status, so I guess it's not ready yet. we are all waiting for this JSR to complete in order to implement WebSocket in a standard way. But we've been deploying, Jetty has been deploying WebSocket since more than 2 years now, and we have very successful, real use cases example. We also have Java clients, so you can actually talk WebSocket server to server very efficiently. 60% of the worldwide clients have a browser or client that is supporting WebSocket, so that's good. So WebSocket is here now. Just use it. Use Jetty. Support is production ready, so just do it. What are the limitations of HTTP of WebSocket? Well, first of all, WebSocket is a very low-level protocol. It doesn't carry the semantic that HTTP carries. I'll give you an example. If you read an HTTP response, you can actually go and say, what is the content type of this response? Oh, it's image/PNG. So the bytes that follow, you actually know that these bytes is an image in PNG format because HTTP carries additional information to its packet, which is totally absent in WebSocket. Okay, so you say, okay, I'll start, building my own protocol on top of WebSocket. Then you start adding authentication. It's already there in HTTP. You start adding heartbeat to keep the connection alive in order to not getting close by intermediaries. You start adding other features. I want to specify additional information about the stuff that I'm sending over WebSocket. Well, you soon realize that basically you're building another protocol on top of WebSocket for your application. So our recommendation is don't do this. Look around. There are plenty of libraries. Comedy is one of these libraries that give you a higher level way of dealing with WebSocket. What if the client doesn't support WebSocket? What you have to implement is a fallback mechanism to fall back to HTTP, and you have to do it on your own. So again, Comedy, for example, takes care of this. If WebSocket isn't well supported either by the server, by the client, or by any intermediaries in the middle, it falls back to HTTP. One second. All right, so with this, I'll leave the, we'll take questions later if you don't mind. I'll leave the word to Thomas, we'll be talking about speedy, which is the new thing. Did you turn on your mic?
It's on already. Is it on? Can you hear me? Very good. So after the nice introduction into web history from Simone, we come to the very interesting part of this session. We talk about speedy finally. So WebSocket has been pretty cool already. So it addresses all the limitations in HTTP quite cool. But the major drawback is that you have to make your application aware of WebSocket. You have to have a client which is capable of talking WebSocket. So you have to have a JavaScript implementation or something like that, which is talking to your backend server. So Speedy, let's start with a small introduction what Speedy is. So Speedy is a live experiment developed by Google. They started like 2.5 years ago to address all the current limitations that HTTP 1.1 has and that Simone just outlined so nicely. It is designed to be faster and better than HTTP, and it's quite successfully doing that. It's already widely deployed, so even if you don't recognize it yet, or even if you don't know it yet, you might have already used Speedy, and I guess most of you have already used Speedy without even knowing. All the current browsers, except of one, you can guess which one, on the desktop are already capable of talking Speedy, and if you use Chrome, Firefox, any recent version, or even 1-year-old versions, and talk to a Google backend like Google Mail, Twitter, our website, for example, other big pages, you have been already using Speedy, and you've already gained all the benefits I will outline in a minute. The Speedy protocol is a binary protocol which will replace HTTP on the wire. So, but it will carry HTTP over Speedy, so the semantics of your application won't change. It's also capable of carrying other protocols. So if you can think about transporting WebSocket over Speedy, or even other use cases. You can nearly any protocol can be transported over SPDY if it makes sense for whatever reason. So SPDY uses TLS as the baseline protocol, so everything is encrypted right now. This might change when it will get HTTP 2.0, it might not, we will see. It's basically a new framing protocol over TLS, and as I already said, it will use the existing HTTP semantics, so you will have still your GET request, your POST request, your HEAD request. It will be completely transparent for your application, which is the most cool thing about SPDY there is. So SPDY is a binary protocol. It's slightly more expensive than WebSocket, really slightly more expensive than WebSocket. It's faster than HTTP to parse because it's made to be parsable as easy as possible. So it's really easy to implement a parser for SPDY frames. It's built to carry HTTP as said, but it can take other protocols as well. So this is basically how it works. There we go. This is the TCP connection. Here's the client, here's the server side. In SPDY, when the client wants to request something, it will have to open a SPDY stream. It's doing that by sending a SYN stream frame, including the HTTP request, as you know it. It's a simple get/HTTP11 request, as you've already seen it in your HTTP application, probably. It will send it over the SPDY connection. The server will get it. The server will calculate the response. It will send the HTTP response in a SYN reply frame, it's so-called, 200 OK, so there's content. And then it will send the body of the response in a data frame, or if it's a bigger body, in multiple data frames. So there's not much benefit visible here yet, but the big benefit comes now. SPDY is full multiplexed. In HTTP, you have a single request from the client, you send it to the server on one connection, you have to wait for the response, and once you got a response, you are able on this connection to send another request. Not before. So you always have to wait for a response before you're able to send the next request. While the server is waiting for the next request, it's doing basically nothing. With SPDY, you can send multiple requests at the same time in a different or in whatever order you want on a single TCP connection. So it's fully multiplexed. You see there's a SYN stream here, which is sent a bit later than this SYN stream here. And you also see that the responses are not sent in order back to the client. So this response here is the second one. This response is the first one because it was calculated much faster. This response was probably quite expensive on the server. So the server needed more time to respond to that one and was sent last one. So you don't have to wait for anything. You reduce the wait times on the server and the client. You get your data much faster to the client. Pretty cool stuff. Now it doesn't work anymore. This again. Okay, so as I said, multiplexing, biggest benefit of multiplexing is that you make a way more efficient use of your TCP connections. Instead of using 6 TCP connections as current browsers do for a single client, and with domain sharding maybe 12, maybe 18, depending on how many domains you use to hack this, you have one connection. Using less memory, using less file descriptors, using less resources on the network and everywhere. So you save resources on the client and on the server. As Simone already outlined, if you have 1,000 clients concurrently online, it makes a huge difference, believe me. It also reduces TCP slow start. So if you have a very fast network connection, with TCP, it takes time until you can utilize the full bandwidth because there is a window size, and this window size on the first packet is really small. You have to wait for the first response, then the server can double the window size, and it takes a huge amount of packets back and forth until you utilize the full bandwidth you have. When you start with SPDY and you send multiple requests at the same time, you don't have to wait for any response to increase the window size. The window size will be increased way faster than with traditional HTTP. And you're getting way faster to use the full bandwidth you have. And we will see it in our demo later on, how big that improvement can be. So, yeah, the response, maybe our center of order, I've already told that. The key point of all this stuff is we want to reduce the round-trip waits. And I will get to that in a bit more detail in a minute. So SPDY is built for HTTP, as said already, can carry other protocols. Another big benefit of SPDY is HTTP header compression. With HTTP, we have a problem. The overhead, as Simone already told, of sending an HTTP request is usually way bigger than what you already want to ask the server. So you send lots of HTTP headers for a really small request you need. And on subsequent requests, even worse, you have to send the same request headers and response headers again and again and again for every request because of some limitations inside HTTP. With SPDY, you have first of all header compression, so you don't send the headers in plain text anymore, you compress them. That already saves you like 25% of the data you have to send over the wire, which is quite a big improvement already. But on subsequent requests, because with SPDY you have streams and you have a single TCP connection, you don't need to send the redundant headers again and again and again, because the server already knows for this connection what headers have to be there. You save 80% and more on every subsequent request. Just to give it some numbers, we've taken our own website, which is website.com. With HTTP, 568 bytes of header data for a simple GET request. We just want to tell the server, get me that / page. With compression, we have 389%. So that's only 68% of the original HTTP overhead we have already saved just by compressing the headers. For subsequent requests, we have to send 26 bytes. 26 bytes instead of 568 bytes for every stupid request. I mean, that's a huge improvement. It's 4.5%. 4.5% instead of 100% of data over the wire. And that's for every request, every subsequent request. So the saving is really big. It's especially interesting if you pay for your traffic on Amazon EC2 service or whatsoever, but also for the performance benefits you get. Another very impressive feature of SPDY, and maybe the most impressive one there is SPDY Push. And we will see it in our amazing demo, how big the difference can be with Push. Push enables the server to push resources, files, whatever, to the client without getting a request for the resource. So for example, if you request an index.html page, this index.html page usually leads to lots of images being loaded, lots of JS files, CSS files, all of them have to be sent to the client, and all of them have to be requested by the client first. So the client gets the index.html, and after it parses the HTML, it knows more files it needs, it will have to request them, and I will get to that in detail in a minute. And with SPDY Push, the server might already know what resources belong to a client's request and will push them without the client having to request that stuff. And that makes it way faster because you save a lot of round trips from the client to the server and back. With Jetty, we are one of the first who have implemented the SPDY spec in Java, and I think we are the first who have implemented a decent, fully automated push strategy, which is, again, completely transparent to your application. So you don't have to touch your application. You just do 3 minutes of Jetty configuration. You get all the benefits from SPDY, and you get all the benefits from SPDY Push. I won't go into detail on this, but we use the referrer header and the if modified since header to detect which pages or which sub-resources belong to a certain main resource. And that works pretty well. So we've done some tests, and we have it live on a couple of sites, including website.com. It works really, really well. So how does the benefit work in real life? So we have the Chrome client here on this side. Can be a Firefox client, can be Opera or any other browser talking HTTP. We have HTTP 1.1, and we have the server on the right side. First of all, the client requests index.html. When the server has calculated index.html or served a static file or whatsoever, it will send it back to the client. And once the client got it, the client will start parsing that file. Once the client finished parsing that file, it recognizes that there is an application.js file and a style.css file. It has to request to render that full page. It will request both from the server. With HTTP 1.1, it will do it parallel because we have more than one connection open, or we have opened more than one connection. And it will get the responses from the server. Then it will pass application.js and it will pass style CSS. It will notify that, recognize that in style.css there is an image being referenced. So it has to do another request until it waited for the first 3 responses. It will do another request to image PNG. So another round trip, which took time. Now with SPDY Push, the situation is quite different. Again, we have the client, the same client, Chrome. We have SPDY Free plus Push. Now we have a Jetty server with an HTTP, with a SPDY connector configured, and we have configured it to use our push strategy. The Jetty server will, on the first request which come to the server, will build up this cache you see here by recognizing which sub-resources belong to the main resource, and it will know which resources belong to index.html. So the client will request index.html, and the server already knows what the client will need as well. Before the client has to do anything else, it will send all the sub-resources back to the client. And this saves a huge amount of time. This is a very, very small example with only 3 sub-resources. As Simone said, the average page right now has 80 sub-resources. More sophisticated pages may have way more than 80 sub-resources to be sent, and the effect will be bigger the more sub-resources you have. And as you can see here, there's only one round trip. It's one request back to the client instead of a couple of round trips back and forth, back and forth, back and forth, all with network latency in between, slow internet connection, even worse for mobile devices. Pretty cool stuff, pretty amazing. You will see it in the demo. So how much faster than HTTP can SPDY be? So Google did a research. They have all the data available. If not Google, who has all this data? They did a research on the average web page, and they found out that it's up to 25% on this average web pages. But that includes HTTP hacks like domain sharding, and those HTTP hacks and also others will work against SPDY. So if you turn to use SPDY, you have to get rid of the hacks. If you don't, it will still be faster, but maybe only 25%. If you get rid of the hacks, it might be even more faster. We have seen improvements of up to 50% and even more, just by exchanging an HTTP connector with a SPDY connector. And doing nothing, no changes to your application. Just try to save 50% or 25% even in your application. It will be way more work. Yeah, can my JEF application leverage SPDY? Yes. Yes, your application, web application, can use SPDY right now. You don't have to touch anything. All you have to do is 3 minutes of configuration, exchange the HTTP connector of Jetty with a SPDY connector, you are done. If you want SPDY Push, configure a SPDY Push strategy, maybe the one we've implemented, maybe a custom one, another 2 minutes of configuration, you are done. You will gain on the benefits, you don't have to touch anything on your application, which is pretty cool. People now will keep asking me, so what's the drawback? To be honest, I have no idea. It's completely backwards compatible. So if you have an SPDY connector and you have an old browser which is not able to talk SPDY, it will talk plain HTTP on the same connector. Same port, same socket, plain HTTP, old browser, you're done. If you have a SPDY capable browser, you get all the benefits nearly for free. So pretty cool stuff.
Thomas, let's go directly to the demo because we're running out of time.
Okay.
This slide here shows that SPDY is already supported by, go to the next one, please. SPDY is already supported by Firefox, Chrome, Opera. There's a Java client too. On mobile, Android, Chrome, Firefox. 45% of the worldwide clients already are SPDY enabled. If you have a Gmail account, you connect to the Google server, you're not speaking HTTP anymore. You're talking SPDY to Google servers, YouTube, Calendar, Reader, Gmail, anything, translate, search, whatever. If you connect to Twitter, SPDY again. Webtite.com, SPDY again. There are a number of sites that are growing, deploying SPDY for this.
And it's getting more and more browsers every day. So
Absolutely.
with people updating their browsers with modern browsers automatically, it's getting more and more widely used.
This is your demo, Thomas.
As well. So we have a SPDY demo. The demo is pretty cool, and I hope you will like it. I guess you will do, but let's see. So first of all, I have to find the mouse pointer.
Sorry. It's on the other window. Yeah. I'll help you out. You speak, I type.
Yeah, you speak, I speak, you type. Even better.
Here we go.
So we will do three things. We will do an HTTP request, traditional one. You will see what we will get as a response in a minute. we do a SPDY request, and we do a SPDY push request.
Okay.
So first of all,
pay attention.
First of all, we do the HTTP request. Simone, your turn.
Pay attention.
So wow, that was pretty cool and fast, huh? The image was there instantaneously.
To be honest, what we did was we artificially slowed down the localhost interface in order to, increase the latency between the client and the server, because otherwise over localhost this would be really fast. So we are simulating a real experience on the web, on the internet, right?
We have used like 50 milliseconds of latency, which is pretty average for an internet connection. So we're not faking something really slow, but we use actually, it's already a fast internet connection with 50 milliseconds.
Have you seen how at the very beginning the images were coming down, pop, 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 but then at the end was pop, 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 like
that
this?
Was TCP slow start, my demo.
This is TCP slow start in action, okay? And it's an effect that you actually see. It's not, something that you don't see it.
My demo.
Sorry. All right.
So you've seen TCP slow start now. So now we do the same thing with a fresh SPDY connection. Again, we are having, for this demo, we have 3 different connectors. One for HTTP, one for SPDY, and one for SPDY plus push. So each initial request we do will be the initial request to this connector. So the browser will have to open new connections and stuff like that now again. So Simone, your turn. So that was already quite a lot faster, just by changing from HTTP to SPDY. We mitigated the disadvantage of TCP slow start on the first request over these connections, and it was already way faster. If Simone now reloads the page, we have the connections already ready. It's, again, way faster. You don't have to measure the difference, you just see it. Anyone who didn't see it, then we do it again. Okay. And if you feel a difference that huge, and if you can feel it, then the difference is really big, because otherwise you have to measure performance to see like 10%. 10% you don't feel it. But if it's bigger than that, you definitely feel it, and I think you have seen it. So now we do SPDY push. And now I need everybody to turn right and wake up your neighbor, because I will be asking questions. Simone will now click on SPDY plus push, and I will ask questions. Simone. Wow, who noticed the difference? Who did? Very nice. You've seen ghosts, I think, because that's pretty much the same as we have seen with SPDY. It's TCP slow start, as we had to open new connections, and it was the initial request, so the server has not been aware which resources belong to the sub-resources. It had to build the push cache, I explained a minute ago, internally on the first request, what we have done now. Now, I will do a countdown for Simone to click, because otherwise you won't notice. So now comes SPDY with push, and Simone will click in 3, 2, 1, now please. That's it. Simone, do it again. I mean, if that's not amazing, click. I have no idea. I mean, you don't see. Before you have seen all the single images appearing one by one, one by one, one by one. If you now click it with SPDY push, one round trip, everything on the same page again. And this is, again, it's a very simple example. It's just a couple of images. It's not 80 resources as on the average web page, or 100 and couple whatever on a sophisticated web page.
And pretty before cool you actually ask, nothing is cached. We made sure that all the responses that we pushed to the browser were not cacheable. So
5 minutes to go.
Yep. Okay, let's go back to the final things. I guess, Thomas, you're...
Yep. And you have to be fast.
Ooh, I need to really be fast.
I'm sorry for being too slow, but only a little bit.
All right, so let's go for the conclusions here. SPDY is there already. What about HTTP 2.0? So HTTP 2.0, the work on it has already been started. There were a couple of proposals for what could be the next HTTP protocol version. One of them was from Google, with SPDY, and the other one was from Microsoft with a proposal based on WebSocket Framing. The big difference between the two is that SPDY is already deployed, the other protocol was not. So easy choice. SPDY was chosen as the basis for HTTP 2.0. So the future is SPDY. There will be some changes. It will take probably a couple of years for the HTTP expert group to actually figure out all the details of the specification, but eventually will come. So, conclusions. The web is evolving. Content grows. Network capacity also grows, but not at the same speed. It is going to be to stay in the back, and plus it's limited. Try WebSocket today. Jerry is deploying WebSocket since 2 years. Try SPDY today. The SPDY implementation in Jerry is 1 year old, and we have people that actually uses it. Ourselves, we are using it. So you have to check and be prepared. The SPDY is there. Any one of you is using Jerry for testing but not in production, I'll tell you this. Salesforce runs Jerry. LinkedIn runs Jerry. We have the largest chess client, chess website running Jerry at a rate between 9 kilo and 11K requests per second without breaking a sweat. So Jerry is production ready. And we've seen, I'll show you performance graphs before, where Jerry can do actually up to 40K requests per second. So it is production ready. Are you? That's the point. So you can actually have a preview of HTTP 2.0 today. Do it. Couple of references. We're going to kind of pick up the winner here. I think we're a bit late for question and answer, but we'll be outside if you have any questions here. Thomas, I'll suggest we throw the box on the floor.
I already choose one.
Oh, okay.
The thing is, I would have liked to do it in front of you, but we have to hurry, so I just choose one. I'm now checking if he put 2 cards in, because if he did, he has to pay the device instead of getting it. And if he did, I will choose another one. Try to be real quick. By the way, such a nice company we are. If you have really...
You lost one. You lost one.
Yeah, I don't care, because I just have to check if it's double ones. As we are a really nice company, if you have compelling reasons why we should show you how nice our support is, you can get a free hour of developer advice support from us. Just let us know your reasons. If they're good enough, you will get a business card from us. We will get your business card, and you get a free hour of our service for free.
Oh, you're counting them?
No, I'm not counting. I'm just checking if you put twice in. There might be clever
there's
people.
There's a lot of people, come on.
There might be clever people.
Do some like kind of Monte Carlo stuff and...
Yeah, just to be safe. So the winner is Robert Olson from Sogeti.
Yoo-hoo!
So Robert, just get back to me. I have the device in my room, so I have to pick it up for you, so we'll meet each other somewhere. You are. Perfect. So again, if you have questions, just get back to us outside. If you have compelling reasons for developer advice, you can get a free hour from us.
Thank you for coming.
And thanks for coming. Hey, Simone, we kicked ass.
Oh,
very good.
Oops.